Hi, welcome to MooMooMath. Today we're going to work on day 2 of our trig identities unit. So we're going to go over the topics of odd even, we're going to look at factoring, and we're going to look at co-functions, as well as do some more trig identities. So in order to do these, let's first talk about factoring. Okay, factoring a trinomial. What multiplies to 24 and adds to negative 10? And just factoring, that's going to be x minus 6 times x minus 4, because the product of negative 4 and negative 6 is positive 24, and the sum is negative 10. Now, that's the first one. That one's pretty easy to see. But what happens if we have a quantity? Well, how is this one going to factor? So we have x minus 3, quantity squared, minus 4 times x minus 3 minus 12. So this works very similar to the previous one. We ask ourselves what multiplies to negative 12 and adds to negative 4. And the answer is negative 6 plus 2. So this one's going to factor into a negative 6 and a positive 2 as our two back terms in our binomials. But what is in the front? Well, it's the square root of x minus 3 squared. So this is just going to be an x minus 3 as a quantity. And this one's going to be an x minus 3 as a quantity. Now, both of these simplify. So that's going to be an x minus 9 times an x minus 1. And there we go. And that's how this one factors. So it's just a little more creative in the factoring. Now, I hope you remember how to factor the ones that have a lead coefficient of, that's not 1, in this case it's 2. So I tend to use the A times C method, where I multiply the first term times the last. This one is fairly simple, so you could probably use guess and check. But I'm going to multiply 2 times negative 9 and get negative 18, and ask myself what multiplies to negative 18 that adds to negative 3. And that's a positive 6 and a negative 3. So I'm going to take my middle term. I'm going to rewrite it. So I have a 2n squared. It just comes down. I'm going to rewrite 3n, positive 3n, as positive 6n minus 3n. So I'm just rewriting the middle term as the sum of two terms. And bring down my negative 9. Now this just factors by grouping. So let's take our first two terms and factor out our GCF, which is 2n, and that leaves us with n plus 3. And then do the same thing with the back. A negative 3n minus 9, factor out a negative 3. If this third term is negative, always factor it out. And that's going to be n plus 3. So the two factors are 2n minus 3 times n plus 3. If you've never factored this way, really the easiest way to see this is factor out that n plus 3 first, and you're left with 2n minus 3. So that's how that one factors. So we're going to be doing some factoring with trig functions. So let's see what it's going to look like to factor with trig functions, and my students are going to have several problems on this in homework. So let's start off with one where we've got a sine squared x minus 3x sine x minus 10. So we just really need to look at this kind of like it's just a regular trinomial. So I'm going to replace sine with a y. So what if I say sine x is equal to y? Then I would just have y squared minus 3y minus 10. And then you can see, oh, this is just a trinomial. So how's that going to factor? Well, what multiplies to 10 that has a difference of 3, and that's a negative 5 and a positive 2. And then I'm just going to have a y and a y. But we're going to replace these y's with what we define y to be. In this case, it was a sine x. So it's sine x minus 5 and a sine x plus 2. Now, if you don't have to do that step where you substitute, that's fine. And maybe after working it a few times, you'll see that, oh yeah, I can see that now. But this is where you're going to stop. All we're doing is factoring. So you're done once you get to this step right here. So let's try this one. We have 5 minus 4 cosine x minus sine squared x. Well, I hope you're looking at it saying, okay, this one has a problem. I have a cosine and I have a sine, and I can't factor with two different trig functions. That's like saying cosine is y and sine is z, and I can't factor that. So what we have to do is we have to use identities to replace one of them. So I'm going to take this sine squared, and I'm going to use a Pythagorean identity to replace that. So we know sine squared x is equal to 1 minus cosine squared x. Now, if I can replace that sine squared with anything with cosine, I've now got it speaking to each other in the same trig function. So let's do that. Let's do 5 minus 4 cosine x minus, and remember this is a quantity, so 1 minus cosine squared x. So I've replaced sine squared with 1 minus cosine squared. Now let's just simplify. Because this is a negative, I have to distribute that negative in. So I get 5 minus 4 cosine x minus 1 plus cosine squared x. Well, that kind of helped us because our squared term is now positive. So let's put it in standard form, which is cosine squared x minus 4 cosine of x, and then 5 minus 1 is plus 4. Okay, so now we have it in standard form. How is this going to factor? Well, if you're having trouble seeing it, again, define y is equal to cosine of x and replace the y's in here. I'm going to try it without doing it this time. So I'm asking myself, what multiplies to positive 4 but adds to negative 4? Well, that's just a negative 2 and a negative 2. So that's how it's going to factor. So what is the square root of cosine squared? Just cosine. And there's my factor. I'm done. I'm done factoring. You can also write it as cosine x minus 2, all quantity squared. Now, excuse me, let's look at some odd-even functions. Odd-even functions we kind of have defined algebraically. So let's look at the algebraic representation and then the graphical representation. So algebraically, what are we doing with an odd function? Well, f of negative x is going to be equal to negative f of x. So if we plug in a negative value, we get out a negative value for the positive x. So when we have the opposite sign of values, so let's say we plug in negative 1 into a function and positive 1 into a function, you get opposite outputs. So if you plugged in negative 1, positive 1, you get out 5 and a negative 5. Those are odd functions. They're even if you plug in a negative 1 and a positive 1 and you get the same output. Those are even functions. So graphically, what does an odd even function look like? Well, let's just stick with some easy ones. Okay, a cubic function. A cubic function looks like this. Okay, it's an odd function. It's rotational about the origin. Therefore, it's an odd function because if I plug in the value 1, I'm going to get 1. If I plug in negative 1, I'm going to get negative 1. So when I plug in 1 and negative 1, I get opposite signed outputs. That's what an odd function is. So let's look at graphically what an even function looks like. A parabola, the parent graph of y equals x squared, that one's an even function. That's when it's symmetric over the y-axis. So if I plug in 1, I get out 1. If I plug in -1, I get out a +1. I get the same output. So opposite values, a 1 and a -1, but I get the same output, same sign outputs. So there's my odd even, just review. Okay, so which trig functions are odd and even? Well, your odd functions are sine, cosecant, and they go together, so that makes sense. Tangent and cotangent. Your even functions are cosine and secant. So let's just take a look at each of the graphs so you can kind of see those. Okay, let's look at sine for a minute. Okay, if we do the first period of sine, there's our graph, and now I'm just going to graph it backwards so you can see it. Now you can see this is rotational about the origin, and this minimum would end up being that maximum, and this maximum would end up being that minimum. So it is indeed rotational about the origin. Okay, that is your sine function, and it is odd. Cosecant, of course, would be the reflection. So your cosecant graph looks like this about the origin. And again, you can see, well, if I rotated it, this branch would be down here and this branch would be up there. It would indeed be rotational about the origin. So there's your sine and your cosecant, so you can see the visual. Let's look at tangent. Okay, tangent looks like this. It kind of looks cubic, but remember it's not because it's got asymptotes. Okay, but you can see indeed it is rotational about the origin. That's a very easy one to see. So that's your tangent, and it's going to be an odd function. Now cotangent, a little bit harder to see, but remember, you've got this and then the other curve on the other side. Okay, if you rotated this about the origin, boom, it's going to land here. This one's going to land up here. This one's going to land down here. It's rotational about the origin. Okay, now let's look at a couple even graphs just to refresh. Cosine. Cosine, one full period starts at 0, 1, and there's a period. Now, if I go backwards into the back quadrants, boom, and you can see, yeah, that's symmetric over the y-axis. So it's an even function. And then, of course, secant would be the reflection. So if I reflect this up and reflect this down, reflect this one down, okay, reflect this one over here, you can see, yeah, that almost looks like a parabola, but of course we know it's not because it, again, has asymptotes. But you can see it's reflecting, and these would reflect over the y-axis also. So those are your odd even functions and kind of the visual. So when you plug in a negative value into sine, that is the opposite sign of a positive value. And then for cosine, when you plug in the negative angle, it's going to be the same as if you plugged in the positive angle. And we're going to look at a couple of those as to why and how. So these are what we call cofunctions. Sine and cosine are cofunctions. They are shifted 90 degrees off each other. So the sine of pi halves minus the angle u in radians is equal to the cosine of u. And the other way around, cosine of pi halves minus u is equal to sine of u. That works with tangent and cotangent because they are cofunctions, secant and cosecant because they're cofunctions. So I'm just going to sketch a sine graph for a second so you can see it and see what I'm talking about, the 90 degrees. There's your sine graph. And what do we know about cosine? it's 90 degrees off. And if I take, I didn't curve it quite enough, but if I take those and I shift them, they land on each other. They're just shifted by 90 degrees. So you can kind of see that shift. Whoops, it's supposed to be erasing here. Okay, the same thing works for tangent, cotangent, and secant and cosecant. Secant and cosecant are pretty easy to see. Here is my cosecant graph. Okay. And then if I take that and I shift it, it's going to end up being my secant graph. Okay, if I just shift it over 90 degrees. Just a way to look at it. Okay, so let's prove it with some numbers and looking at the unit circle. So the sine of 30 is equal to the cosine of 60. So let's look at that. So what is the sine of 30? Well, that's a half. What is the cosine of 60? That one's a half. So they're both 1/2 because it's the difference from 90. They're complementary. So the sine of 90 minus 60 is equal to the cosine, I'm sorry, the cosine, I'm sorry, I did that right. The sine of 90 minus 60 is equal to the cosine of 60 because that would be the sine of 30. So you're just looking at the relationship of those complementary angles. So let's take the tangent, let's say the tangent of 90 minus 60. That's going to equal the cotangent of 60. So the tangent we would then evaluate at 30. What is the tangent at 30 degrees? Well, that is the square root of 3 over 3. And what is the cotangent of 60 degrees? Well, that is your root 3 over 3, which remember, cotangent is your cosine over your sine. And that's going to end up being, I'm sorry, I did that backwards. I just wrote the tangent instead of the cotangent. The cotangent is going to be your x over your y value, which is going to end up being 1 over root 3, which we know simplifies to root 3 over 3. And so those two are indeed equal to each other. So that's what it means to be a co-function. Okay, so let's write some true co-function statements. The sine of 65 is equal to the cosine of 90 minus 65, or its complement, which is 25. So that's going to be the cosine of 25 degrees. Tangent, a true cofunction would be cotangent is equal to 90 minus 20, which is cotangent of 70. There's a true statement. Secant, its cofunction is cosecant. So what's 90 minus 42? And that's going to give me 48. So that's going to equal the cosine of 48 degrees. Okay, pretty easy to see in degrees. Now let's look at it in terms of radians. Okay, cosine's cofunction is sine, but I have to take pi halves because we know pi halves is 90 minus pi eighths. And so that equals the sine of 3 pi eighths. Still the same thing, you're just evaluating it in radians. And then cotangent, I'm going to take the tangent of pi halves and subtract 3 pi halves to find its complement. We did complements at the beginning of the trig units. And that gives me, what's that going to be? 3 pi 6 minus 2 pi 6, so pi 6. And there you go. And there's the other cofunction. So you can just find them by subtracting from 90 to find the complement, or subtracting in radians from pi halves to find the complement. Now, there's those answers if you need those. Let's just prove it. Let's just show it. Okay, so let's evaluate and use our unit circle. So the cosine of pi over 2 minus pi 6, we're going to evaluate this for pi 6, is equal to the sine of pi 6. Okay, what do we know the sine of pi 6 is? Well, that's on the unit circle, right? Boom, here, our very first spot. The sine is 1/2. Now, let's take 3 pi 6 minus pi 6, and that gives me 2 pi 6, which is pi thirds. Subtracting that. So what's the cosine of pi thirds? Well, that's, boom, right here. We know that's also 1/2. So there we did. We just showed that those two were actually the same value. Okay, now we're going to do a little bit of proof practice today. We're going to use all the proofs we've learned, all 17 that we did yesterday, plus our odd evens. So let's try a couple. Okay, this first one is just a simplified problem. So we're not trying to get to something other than a very simplified expression with trig values. Okay, 1 minus sine squared. I have a sine squared, so that's got to be one of the Pythagoreans. And remember, we have the form of cosine squared x is equal to 1 minus sine squared x. Okay, you need to have those handy as you get used to those. So that means I can replace 1 minus sine squared with a cosine squared x. Okay, cosecant squared x minus 1. That's also another Pythagorean identity. That was one of the forms we did yesterday. And I'm going to scroll all the way back to that identity from yesterday. And let's see where those are. I wrote all 8 of those up here. Okay, here we are. So cosecant squared minus 1, that's equal to cotangent squared. So I can replace cosecant squared minus 1 with cotangent squared. So let me see if I can get there a little faster this time. Here we go. We're all the way down to here. Okay, so I can put a cotangent squared x in here. Now I'm in terms of cosine and cotangent. I want those to talk to each other. So I'm going to rewrite cotangent in terms of sine and cosine. So I have a cosine squared. It's already back to the basics, sines and cosines. But cotangent is going to be cosine squared x over sine squared x. Now I end up with this complex fraction. So what do we do with complex fractions? We keep the first one, that's cosine squared x all over 1, and we're dividing it by the second one, cosine squared x over sine squared x. Now, if you remember the keep, change, flip rules, right? We're multiplying by sine squared over cosine squared, so that's going to be cosine squared x all over 1 times sine squared x all over cosine squared x. Use our algebra skills. Same factor, they cancel out. Same term, excuse me, same terms. So I end up with just sine squared x. So there's my final answer, sine squared x. So this big term simplifies to just simply sine squared x. There we go. So there's one of our identity, or one of our trig identities where we're just simplifying. Now let's look at some odd even ones. So what are odd evens going to look like? This is what they're going to look like. So let's say you have a negative cotangent of negative x times a sine of negative x. So you got to use your odd even identities. So this is another set of identities you can now use to simplify. Well, cotangent is an odd function. So I know that cotangent of negative x, this portion is equal to negative cotangent of x. But then I have that times a negative 1, because really that's just a negative 1. So this portion of the cotangent part is actually a positive cotangent of positive x. Now let's look at the sine part. Okay, sine is also an odd function, so I can replace sine of negative x with negative sine of x. So that's times negative sine of x. So what does all this simplify to? Well, negative cotangent of x times sine of x. So the term is actually negative. Now I can simplify this a little bit more because I know cotangent can be replaced with sines and cosines. So that's going to be negative cosine of x over sine of x, and these aren't squared, so they're just simply cosine and sine, all over sine x, all over 1, and then the signs cancel. And what am I left with? Negative cosine of x. And there we go. There's our final answer. Now, some of you guys are going to want to shortcut and do things and not write every step. You need to show every single step to show you're using correct substitution or you're simplifying these odd even functions correctly. You want to show every single step. And boom, I'm done. It's simplified. And there we go. So we're not going to have a quick quiz tomorrow, but we are going to work on worksheet 2. Worksheet 2. What you need to know is you need to know how to factor with trig functions. We did that at the beginning of the lesson. You need to be able to identify odd even and use those in a proof. That last one we did, we just used it in the proof. And we need to understand co-functions, how sine and cosine are co-functions, secant, cosecant, tangent and cotangent, and then just simplifying those in proofs. So you can use those identities sometimes if you need to. So there we go. Worksheet 2 is what we're working on. Over factoring, odd evens, and a few more proofs. Keep in touch. Let me know if you need some help.